Hello everyone. Today we're going to talk about the Alternator project, and this here is a welded assembly, and we want to apply geometric tolerancing to it. And I'm sure everybody is familiar with an alternator. You probably placed one on your car some time ago. And this is a sample of the alternator bracket we have right here. You notice it's a welded assembly, and this welded assembly has a number of components that are all welded together, and we would like to be able to tolerance this assembly. You have the details, so we're just going to tolerance the assembly. The details would be done something separate, but I included all the details in the assembly. Let's take a look how the part works. It's important. What we have here is an engine. This here is the front view of an engine. This here is the side view of the engine. You can see this front view of the engine. There's the harmonic balancer. It looks like I have a belt that goes all the way around, goes around the alternator, up looks like around the air pump, a couple of other things here. We have a belt tensioner that's over here. And this alternator bracket, the alternator was down in an area where it was interfering with the bracket. So what we wanted to do was raise it up. And this alternator bracket raises up an existing alternator up a little bit higher. To maybe explain that a little bit better, let's take a view of that. We'll just take a cross section of that view and blow it up. Now we got a better picture of what that thing looks like. And you can see here's your alternator, mounts down here in this view. This is the old place where the alternator mounted, down on this bracket over here, and all we did was mimic it up here again. See, the alternator did mount down. Now we have this bracket mounts on that spot. It comes up, and this mimics the old bracket. It comes through, and then it bolts on. And then in this view, you can see here's your bracket. This is where it bolts on. This is where it bolts to the alternator. And to keep this whole assembly from rotating back and forth, what we have is we have a bolt on the engine, and that bolts it on the engine. So that stops the rotation. You can see the size bolts we have. These are M12 bolts. Bolts down on the bottom, all over, we have M12 bolts. You can take a look at your drawing, your detail drawing, and assembly drawing and details, and it'll give you a little more information. Let me show you a little bit more how this thing works. Now that you have an idea, this is your bracket, and the way it fits on is it fits on to the mating part like a saddle. It fits over here like this, as you might imagine. Now you can imagine if I just took a bolt here and I tightened it up, this here is just some awful thick material, so you wouldn't be able to bend this thing. So they have an ingenious method here. They have just a sliding bushing. Bushing looks something like this. You put it inside of the hole, and as you took the part in and you tightened up the bolt, the nut would come on this side and then it would slide up. Can you see how that would slide up against the saddle and tighten it up? And the alternator would have a similar device here. So what it's doing is it looks like it's pulling it up against this face on the engine, and then it looks like it pulls up the alternator up against this face over here. And then remember what this one does. So it really mounts, I guess, something on these holes, and then what stops rotation, it looks like this bracket here, so this alternator doesn't take off in any place. This is the detailed drawing of the part, and what I would like you to do is apply the geometric tolerancing as you think is necessary. You can apply it to the 3D part, or there's a 2D you can apply it to, and do the best you can. What I'd like you to do is do the whole job. You ought to be getting pretty good at this point. I want you to be able to select the datums, and I want you to be able to apply any geometric tolerancing, position, perpendicularity, if you have flatness, you think anything that you need, do the best that you can. Now you have all of the detail drawings too, if you look a little later in the text, but we're not going to do all of the details. The way I would always do it is tolerance the assembly. Tolerance the assembly what you want, and then if you want, you could go back into the details and tolerance the details. But at this point, we're tolerancing the assembly, the finished final assembly. So if you could pause it here, give you a chance to apply the tolerancing. When you think you're ready, push the button. I'll be back. All right, we're back. You pushed the right button, here I am again. What we want to do is take a look at our alternator bracket, and I'll show you what I did, some of the thoughts that I had. Matter of fact, I have two solutions. You can pick from those two solutions. My idea is this is geometric tolerancing is just tools, and you decide, you're the engineer, you decide what you want to do. These are geometric tolerancing is just tools for how you want to do it. So this isn't how you would do all alternator brackets. It's whatever you think. There's Fords and Chevys and Toyotas and Subarus, and everybody's got a different idea what makes a good bracket and what makes a good car. So You make your selection. I'm just providing you the tool. So let's take a look at our assembly here. And as I mentioned, what we're going to do is we're going to tolerance this assembly with all of the components all together. The final assembly, what do we want this final assembly to look like? So on this one, the way I saw it, the way the part mounted is it mounted on those two holes. If it mounted on those two holes, that's what set the attitude of the part. And that's what set it back and forth. So what I did is I called both holes datum A. Now when I called them both datum A, you know, we've done that in the past. I have no datum. There's not in relationship to any datum. What I just have is I have two holes, and I want them in line within 0.15. And you know how that would work. Let's say that I have an axis, and my axis looks something like this. I have an axis. If you can see that, make that a little bit bigger. There's a datum axis that I have. And then when I said that both of them were supposed to be positioned within 0.15, they're shown in line, so they have a basic dimension of 0. If they have a basic dimension of 0, I have a tube of tolerance on this side, and that tube of tolerance on that side is 0.15, and the tube of tolerance on this side is 0.15. So all I've done is mathematically establish some tolerance zones, and now the axis of the features have to fall inside of those tolerance zones. And if they fall inside those tolerance zones, they're good. So this here is unusual. If you notice that what I have is two holes that are different sizes. Now we've done it with one hole. There is an option showing you that if you have two holes that are different sizes, I just come in, put a bracket around it, and said both of those, see these two, they're positioned within 0.15. So it's just like if they were the same size. And I call them then datum A. Those two holes are datum A. So you notice on our detail here, datum A, what we've done is we've established the axis on these holes. So I have an axis on these holes, and that establishes datum A. Now do you notice degrees of freedom, what that stops? Stops us up and down, stops us back and forth, stops rotation, two directions. What we need to be able to do now is eliminate movement or translation or movement in this direction. And how I would pick the datum is that when it goes in, how does it fit? Do you notice what it does is when you tighten up this bolt, remember that sliding sleeve over here? It's going to pull it up against that face. So if it pulled it up against the face, the thought was that aligns the part, and then that face stops it back and forth. So I call that face there as a datum face. Right? You can see this is where the alternator mounts on this face. If I call that face a datum, then on the drawing it would show up as datum B. That is the B face. And then on that, of course, to qualify that datum feature, I put a perpendicularity and said it was perpendicular within 0.1 in relationship to A. All right, let's see, what else do we have to do? In order to be able to stop rotation on this part. What stops rotation on this part? If you take a look at the assembly again, it looks like on the assembly what stops the rotation on this whole assembly. I guess you could have picked the alternator, but remember there's leaders and followers, and what I saw is this the leader and that's the follower. This is where it's mounted, and this just follows. That hole will be wherever that one puts it. So I called that one off as my datum C. And then also, do you notice that what I have to do is this face of it, I have to clear this face. So on the detailed drawing, we'll take a look at that detailed drawing, and I called off this face then, or this diameter is datum C. And then of course what I had to do was position it. So I positioned it back to the reference frame, and I positioned it within 4. And if you'll notice, if you've done our calculation, this here would have been a fixed fastener calculation of where I got that number. And you should be familiar with that number by now, how we did the fixed fastener formula. And that's positioned within 0.4 in relationship to A and B, and then I called it C. The next thing, what about that face? That face, where is that face? So what I had to do is I had to locate that face in and out. Remember, if you're located here, fore and aft, then this face will either touch or it could interfere. And we want it probably, the way I would design it, to be on line, in line exactly with that face, or behind. So on the drawing, then, what I did is I put a profile on it. And I didn't put a unilateral or anything. I just designed it, put the basic dimensions on here. So it would come out, so this surface would be in line or back. So I got a possible of a 0.5 millimeter. Do you notice I just put a partial surface here that I tolerance? I didn't need that whole surface, because up here I'm not checking where that arm is. I'm just interested in here it matches with the mating part. So I did a partial datum. Or not a partial datum, but a partial surface that I toleranced. Okay, let's see. Let's take a look back at our assembly, what other requirements we have. Well, another important face that I see that is important is where that face is right there, right? See, this is our datum. It's mounted here. That face here, we told how far it could be away. And now we've got the part lined up. We got it stopped the rotation with our datums. Now we're going about the features and we're telling how much they can be off. One important feature is that face. See, what happens is the alternator comes in and locates on that face. And you can see if that face moves back and forth, well, it doesn't take much to see that that belt is going to misalign, right? Because the pulley's attached to that, and it could misalign. So we want to interested in where that face is relative to our coordinate system to that face. Also, another thing is we're going to want to know where that alternator is up and down. Now, that doesn't matter too much. If that alternator moves around, we got some flexibility in a belt, but we certainly wouldn't want that thing to tilt back and forth. So let's take a look at, we saw some of the requirements on the drawing. Let's look now how I handle that. And this is what I did is I pointed to that face, see, and I profiled it within point 2 in relationship to A, B, and C. So remember, by profiling it, what I'm saying is that face is located within point 2. Remember all the dimensions you will see on the CAD model. This here is just tolerancing. Remember, this isn't a dimensioning and tolerancing course. This is a tolerancing course, and we're looking at the tolerancing. And sometimes this 3D views, it's easier to see the tolerancing. I show it here rather than 2D, as it just seems to come alive. All right, let's see what else we did. Now, another thing is we were looking where that hole is. And that hole, remember what the alternator did is fit into that hole. And wherever that hole was, that's where the alternator was going to be. So on the drawing here, this is the way that I called it off. I said that that hole could be positioned within 1.5. In other words, it could move up and down, and it could move around within 1.5, but wherever it is, it just had to be parallel within 0.4. And across that length, it had to be parallel. And that makes sense, right? It could move up and down, but don't tilt, because if you tilt, that would try and run that belt right off. Now, where I come up with this 1.5, be careful, that was not any kind of formula that you had to position with the alternator. That was just a number. It's just a bolt goes into the hole, into this hole, and it goes into the alternator. How much you want it off, I just said that it was 1.5. So if you allow, for example, on this part, this is where it mounts, and you say that hole can be off, I could have made it off 10 millimeters. It moves up and down, the alternator just finds it. So the 1.5 was how much I would allow the alternator to be off. That would be how much belt I had, how much flexibility I had in my adjustment system. All right, let's continue on. You can see that I'm running out of important things. That was all that was important to me. The rest of this back face, that was clearance. Some of these little edges were clearance. You know, where the back face, that was clearance. So I had a lot more tolerance there. Then I just put a note underneath here, and I says, unless otherwise specified, the profile is 2. So everything else has to be within 2 millimeters. Now, here's another example. Now, this here is option number 2. You notice I put another option number 2, because there are sometimes a couple ways to look at it. And I had some engineers, they said, well, no, I don't think the alternator bracket works that way. And I said, well, how do you think it works? And they said, well, this is the way that I think it works. They said that when you take that part and you put it up, what it does is it comes up against that face. So that means that if you take a look at our alternator bracket, remember, and it was underneath here like this and mounted, and I was tightening up that bolt, and I take this little sliding bushing in here, and as I tightened it up, they said it would pull it up against that face. And they said that that face then, that face is the one that would set the attitude. It wasn't the hole, it was the face. So it's your decision. You're the engineer. If you think that face would be the way it sets up, then that's the one that I would call off as the primary datum. It seems short to me, but then again we have quite a distance between this here that's much longer, but then there was tolerance with this bolt going inside of the hole. So if you think it was the face, then this is the way you would tolerance it up. So there's not a right and wrong way, there's just different approaches sometimes with this geometric tolerancing. So let's take a look at this approach. In this approach, first of all, it said that that face there was going to be datum B. They wanted it to be flat. And remember, the order of precedence of datum is the way they fall inside of the feature control frame. And then what they did is that they took the 2 holes, and rather than just making the 2 holes in line, they positioned the holes within 1.5 or 0.15 in relationship to B. So do you notice what they have is they have the 2 holes in line, and since it's in relationship to B, then they also have a perpendicularity, and then they call the hole datum A. And they clarified it underneath there. See that what they were doing, just so make sure that there was no question of what was happening there. Now let's see, what's next is datum C. And if you notice inside the feature control frame, we positioned it to B and A. So what we're saying is B is their primary datum, A is their secondary datum. So you know that we have to watch the letters in order of precedence in the back here. Here's where they used B as the primary and A as the secondary. And then we call this one off as C. And then I think that you'll find the rest of them will be the same way. You see, this same way, I think that consistent what we did the first time, or maybe just a different order of datums, but this one says B, A, C, then they profile that partial surface just around in that area. Then the next one, it looks like they profile that surface, and that would be the BAC, right? Keep the same datums in the same order. It's going to be the same reference frame. The part only mounts in there one way. And the next one, same thing, what we did before. They allowed the hole to move around 1.5 to BA and C, and then, but they just said make sure the thing is parallel, a little bit better. So that's where we had our parallelism call out. And then here again, we take a look, and this here was unless otherwise specified. Everything else was supposed to BAC, to the datum reference frame established by BAC. Notice what they did is all of these are regardless of size. What they're saying is the hole gets larger. You can imagine on something like this, to me, I would think something like this would be regardless of size. This is not MMC. You can see that, you know, many of the other parts we've done were MMC. So I'm trying to give you some guidelines when I would use MMC and when I wouldn't. For example, we're locating this hole over here. That's where the alternator went. As the hole got bigger, the alternator could be off more. That doesn't make a lot of sense. I mean, we'd be tending to make the hole bigger so it could be off more. And the same thing with these holes. If these holes were off more, then they could be off center more. You know, that would give us more location. The same thing with this one. As this hole got larger, it could be off more. So I would think this here is a regardless of feature size. We're trying to keep things centered. We're trying to keep things on location, as opposed to some of the other brackets. You know, remember like the battery box bracket that we did and some of the other brackets we did. Those were MMC. This here would probably be more a regardless of feature size application. All right, now let's take a look at the details. Now, sometimes what we do is rather than putting tolerance on each one of these, because people say, how would I tolerance the details? These details are shown for reference. They tell you what each one of those details are. We're not planning on it going back and inspecting each one of these parts to make sure it is. When we buy this, we buy the whole assembly. We're buying it all done together, what it's supposed to look like. So these numbers that we give, the numbers on each one of the details, we give them basic. And then when we put our tolerance, remember we put our tolerance unless otherwise specified, everything had to be profiled within 2 millimeters. Well then 2 millimeters in the assembly, everything has to be within 2 millimeters. This radius has to be within 2 millimeters. Everything has to be, so it provides a halo around this thing that it has to be within 2 millimeters. So that means the individual detail, if I was going to make the individual detail, I couldn't allow myself 2 millimeters to make the individual detail, because if I did 2 millimeters, then I wouldn't have any welding tolerance. So I'd probably have to make the details within a millimeter and then give another millimeter for welding tolerance, right? So, and then how would you check something like this? Well, sometimes people say, how would you check all of this? Well, this here is probably, you know, not such an exotic part. We have a lot of tolerance on it. So it's probably setting up with a coordinate measure machine and then randomly sampling certain places and see if they fall within. Probably the first part I would really check very well, and then after that monitoring. If something looks funny, then I would spend a little more time. In other words, you've got to put that information in your quality plan. What's your plan? What points do you want to check? Right? And put that plan out there. Quality should have a plan. Well, what's your plan? You see we can't check everything. Well, then what do you want to check? Put it down in a plan. We'll look at it and we'll evaluate. We say, no, we need 2 more points over here. We have to check these, or less points. We have less problems. We'll relax the inspection. Right? We need a plan. What's your plan? So design has done their job. Now quality has to look at it and say, what's your plan to make sure it falls within? And we know you can't check everything. That's obvious. This here is the detail drawing, and this is the detail drawing. Some of you might have toleranced up the detail 2D. This one here is done in 2D, and if some of you wanted to tolerance this one, allow you to also put the tolerance on that example. And now let's take a look at the option number 1. This was our option number 1, and remember option number 1, what we did there is we called the axis as the primary datum, and then we called the face as our secondary datum, and this hole stopped rotation. And then remember our second option, what we did is we did it just a little different. What we did is we called the face as our primary datum, and then we called the axis as our secondary datum, and then we called this hole is our tertiary datum. So we just, in the two different options, we just switched from the axis of this hole to the face. And you can tell by the way we called it off, BAC. Now this is a detailed drawing. This one here is in 2D. And some of you might have tolerance as 2D example. Let's take a look at how I applied the tolerance to that one. And this is the example showing the 2D example. And let me zoom up on this one and show it to you. This is the example here of the part shown in 2D, how it might be approached. You notice that we called off the datum, and there was this here was our option number 1, I toleranced in 2D. You see the two holes are called off as datum A. Datum B you can't see in this view, you can see it off to the side there a little bit, that's on the side view, and then datum C. In this picture over here, we see the datum B is called off, and then that was where we called off the face. Remember the face, we had a profile within a ½ millimeter, just in that partial area. This is the way it would show up in 2D. And then up in this plan view, this here is where we toleranced that front face, profile within 2. Now what you can do is you can take a look back at the details. You should have the solutions there that you can look at the solutions, and it give you a couple different ways to be able to do it. As I mentioned, this geometric tolerancing is just a tool, and how you want to apply it as long as the engineer has the tools. Well, that completes our alternator problem. Good seeing you again today. Glad you joined us, and we'll see you again for the next problem. Well, welcome, welcome. Here we are again. This is the brake line tube project. And this is your lucky day. You don't have to do any work. All you have to do is just sit here and watch. What I thought I would do is try doing a tube. Sometimes tube, bent pieces of pipe, wire form parts, they are buggers to do. They are very difficult to do sometimes, and I thought I'd show you an example how many times tubes are done. Exhaust pipes, it could be wire form parts, it could be tubes. And let me show you the problem. First of all, we have a brake line tube in this particular case. And this brake line tube, as you can see that where it mounts here. It looks like it's one of these brown ones here, or one of these colored ones. And a tube goes off and it goes up in here into the modulator valve. You know, so this is the tube that we want to be able to tolerance. Now, these tubes are a little bit of a problem. As you can see, I have a little, this here is a little miniature tube that I have right here. And this tube was bent up, as in it took the math data, you know, right from the computer, and I bent it up as best as I could possibly bend it. But what happens during the manufacturing process, you know, that things aren't exactly straight. You see, this tube was supposed to be straight. It's a little bit down. this tube was supposed to be straight, but it's bent off a little in the other direction. This one's a little bent down. Now, how do you check something like that? You can see that's always a problem. You can draw it, but then how do you check it? I mean, that's always our problem is that how do you verify that it's good or bad? You can see if you tried to check it, you hold it down on this side, you see what happens, it flips way up in the air. And they say, well, no, what you should do is hold it down on this one. You hold it down on this one, and then it isn't so far, then this one's up a little bit. You know, or else what I do is I lay it like this, I get this kind of an answer. You know, if I lay this one down, I get this kind of an answer. So I get all different kind of answers, and it's always trying to get the thing in to see what it looks like, and how would you go about doing it? So a way to be able to tolerance them here, this is a fairly common way to be able to do it, and let me show you a tube. This is a picture of a tube, and I'm going to do this one in 3D to show you how it's done, and we'll take a look at the 2D drawing afterwards. But this is our tube. Now what it does is we have a mounting, and if you remember where the thing mounts, it mounts in on this side, so we want to know where this side is going to be. This side here is important because it matches up with something on this side, and it also matches up with something on this side. So what I did is I said, well, this one here was an A-B. If you remember an A-B, that was exactly the same thing that we did when we had a shaft. When we were tolerancing a shaft, you remember, we would call one side datum A and we'd call the other side datum B. And the distance between them, it was a basic dimension. We had a basic dimension of 0. Now what would really be the difference is if I had a basic dimension and I had a basic dimension, the only thing is these were offset a little bit. Then they'd have a basic dimension of 12 millimeters. You say, well, that makes sense. Then all that we would do is we'd build a fixture that would hold this one. Instead of being in line, it would just move over 12 millimeters. Well, now we'd say, well, what we have another problem is this one isn't exactly straight. This one happens to be bent up 3 degrees, and this one happens to be bent down 4 degrees. Now, how could we call that an A-B? Well, how we'd call it an A-B is I have math data where this one is, and I have math data where this one is. So all I would do then is build a little fixture that would hold it at each side, offset at that amount. So that's exactly what I did here. Is that, you know, now when I call that surface off as a datum, you know, first of all, what I did is I said that was only 25 millimeters back. I don't need the entire length of the tube. So datum A is over the indicated length. And look, this here is the datum. It's that long. And over here, datum B, it's this long. That's 25 millimeters over that length. And underneath, what I said is that this was positioned within 1 in relationship to A-B. So if it's positioned within 1, that means that this end here, that distance of 25 millimeters, could move around 1 millimeter, and this side could move around 25 millimeters. So to understand that, let's take a look at the next page here. I've shown a little gauge. And this here, they sometimes call it a ditch gauge because they take the part and they drop it inside of a ditch. And when they drop it inside of a ditch, you see what I would do is I would hold it on this side. I would make an opening for it, whatever size of the tube was, plus 1 millimeter bigger. And then on this side, math data, you give me where that is, and what I'll build is I'll build an opening on that side. And when that side, I open it up, and it has to fit inside of that hole also, and that's 1 millimeter bigger. Now, let's take a look at the next step. The next step is that there's our tube again. We have to be able to stop the movement back and forth. So stopping the movement back and forth, what I did is I called off datum C. I called off that face. That's our datum C. So that's what stops translation back and forth, stops it back and forth. That's my datum C. And now the next thing is we have to stop the rotation on that part. Let's take a look how it mounts. And if we take a look at this picture, we can see that we have a mounting clip, and it mounts right in this area over here. So taking a look back at our detail, you see that what we would do is say that identify that surface right there, and we'd identify that at math data and tell you where it is, give you math data where that was, and we said that that's an area that's 25 millimeters, and we call that datum D. If we call that datum D, that's positioned also relative to that datum reference frame. Now, what I do is now that I have my datums, I located the end of the tube, and I said the end of the tube has to be within 5 millimeters. So that means when that part is laid into the fixture, and you notice how it has to fit into that fixture, it mounts on this area inside that ditch. It also mounts inside of a ditch over here. It's pushed up against that face, and it also has to fit inside of a ditch over here, and that is 1 millimeter. And then this end of the tube, what that is, that's just an end check to make sure that it falls within that within that 5 millimeters. That's a profile, and that's profiling the end of the tube. And then what I did is everything else. All of the other bends, everything else wasn't very important, so you notice what I put down here on the bottom was I put a position. The reason I had to put a position is because the tube has size. If the tube has size, then I have to put a position on it. And I put a position within 5 millimeters. So that means the rest of the spot all around has a position within 5. You can move around 5. I used the word boundary. And the reason I use the word boundary because we want to make sure that it falls within this boundary. And it's just another way, rather than finding the axis of the tube, what we did is we found the boundary of the tube, and it just has to stay inside of that boundary that is 5 millimeters bigger. So if you take a look at our gauge, there's our partner gauge. And you notice that when they check this part, they're not checking every spot all over. Many times on tubes like this, what they'll do is they'll just check the straights rather than going in and checking the radiuses. And you can see these are just random spots across here. I think this was our anti-rotation clip, and the rest of them would be 25 millimeters. And they might check the whole spot or just random spots across here to make sure it falls inside of the tube. This is a cross-section, that what it looks like inside of it. And the reason it looks like that is because it's often easy to be able to build a fixture like that, you know, with square ends. Now, in reality, we know that when you build this ditch, this is a square zone. In reality, this is supposed to be a round zone, but sometimes we build the ditches like this. And you could even build a ditch a little bit smaller to make sure it doesn't go outside of the round zone, or sometimes they let it go outside the round zone. But in theory, it's supposed to stay inside the zone. This here is a 2D version of the tube, and you notice that up on top I have the conversion table. That's a coordinate table, and shows the X and Y data, and all of that information would be basic. And then I put the information on the tube, and let's see, let me call off the datums on here. We'll do like we did before. I call it off down here on the bottom. It's shown on the bottom where I call it off. See, there's my datum. And they identify where those points are. How you want to identify it is not part of this class, but it shows you how the thing is called off on each end over indicated length, and then we'd have to identify what that overall length was. What we have now is we have our datum C, and the datum C was shown off at this edge. And then the next one that we had was the datum D, and you notice that I would have to have some kind of information here. I'd have to give you where that basic dimension was, and it's over that indicated length. That's all basic, so I know exactly where to put that into the fixture. That stop there, there's 1 millimeter. And then, let's see, next what we did is we put the profile on the back. You see there's our profile tolerance, and it points to the back, and what that's doing is that's locating that edge of the tube. So the edge of the tube lengthwise, it has to be within 5 millimeters. And then next what we put on was, so you just put a call out underneath there, and what that one says down on the bottom here, it says that unless otherwise specified, all the tolerance has to be within boundary. And you notice item number 6 there, it says dimensions in a coordinate table are basic, so everything would be basic. And that gives you an idea how we might do a tube. Now what I did is I took the fixture, this here is our checking fixture, and we dropped the tube in, and when it went in, you can imagine how it fit. You see how it's moving around in there? You have to have good eyes to see that, but it's moving around inside of that fixture. And as it moves around inside of that fixture, that has to meet all of those requirements. And that's a common way that we do tubes and wireform parts. Well, that's it for right now. We're finished up our brake tube, and we'll get ready for our next project. Well, welcome to the engine mount bracket. We have another problem for you. This is the house of problems. You need problems, we'll give you problems. This problem here is an engine mount bracket. And it's a fairly simple little bracket, and I thought, well, let's just try and do something simple. This is our bracket. It looks something like this, and looks like it's a machine bracket. And let's say it's something like a transmission bracket or something. It has some holes on the bottom, and maybe it mounts to a frame. And then it mounts something like a transmission, or mounts an engine. It mounts an engine bracket, and all it does is we have a couple of holes in this bracket, you see, and then it's supposed to mount up to the engine and hold the engine in place also. Maybe there'd be some rubber mounting here to hold this next piece up. And this is our bracket. It's kind of a straightforward, kind of a simple thing. And so let's see. Let's take a look at our drawing. Here is our drawing. It looks like our part here. And remember, like I was telling you, it mounts to the frame. And it looks like it's bolted in. We have a nut and bolt application here. And it looks like when it's mounted to the engine or the transmission that's holding it on, probably some shock mount in here, it has some bolts. It looks like it's tapped in. Now, you don't have any information for that tap, so I won't have you do that at all. You know that when you look at those holes, they'll have a position, but how much position, you won't be able to figure that out. But what I would like you to figure out is that we have these mounting holes here, and you can see what size the mounting holes are, and then you can also see the size of the hole and how much position in the frame rail. That's the way it's already coming. We got this from another designer, from the design team. They said this is how much tolerance they've given. This here is your clearance on your bolts. And then it's your job to be able to tolerance your part, to be able to match that. Notice that your holes are different size than what theirs are. They have 1.2, and manufacturing wants as much tolerance as they can on a location of these holes. And other than that, is really not too much. What I'll have you do next is I want you to apply the tolerancing. I want you to select the datums, apply the tolerancing. I want you to calculate that position tolerance and see, give us from manufacturing wants as much as possible from there to be able to make sure this part fits. So I'll give you a few minutes to do the problem, and then just push the pause button or the restart button, and I'll come back again. Okay, welcome back to the motor mount part. I trust that you worked on that project, and now you're looking for the solution to what you did, and compare what I did and what you did, and we'll talk a little bit about it. So let's take a look at the drawing. This was the drawing that you started with, and what I did is I put basic dimensions on. Now, I did this a little different. I put boxes around all the dimensions. Some people put boxes. You could have put that note down here unless otherwise specified. Either way, it doesn't really matter how you do it. This here is just another approach, or just another way to be able to do it. Now, the next thing is I had to select the datums. And the way that I saw the part is it mounted on that bottom face. So if it mounted on that bottom face, I called that off as datum A. And you notice that I also put a flatness on there. I said that it had to be flat within 0.5. So that's my flatness on that surface. Now, what stopped the part from moving back and forth? Well, for sure, it does mount on those bolts. That's for sure. It mounts on those bolts. But what I saw is that also mounted up to this transmission, that I had some math data where that transmission was supposed to be, or that engine was where it was supposed to be. So what I did is I lined it up, and I called that my secondary datum. My worry is that if I call those holes the datum, let me actually put that datum up here. There's my datum I called off as datum B. I put it at that angled surface. And my worry is that if I called off the holes as a datum, which I could have, then I would have put a profile on that face, of course, because I would have had enough datums. Then that means that face was allowed to be off. It could have been off by the amount of the profile tolerance. So rather than doing it that way, I thought, well, what I'll do is I'll take this B face, and I'll actually line it up with that. So it's something like this. You know, I'm looking at setting up the coordinate system on that part. It mounted to the face, and then to be able to line it up this way, what I did is next I picked this as a secondary datum. Now, of course, when it hit that secondary datum, you know, it's only going to hit 2 points of contact, so it's not going to fit tight. So then I had to put some kind of a tolerance on this surface over here. And the tolerance I put on there was just an angularity tolerance. And I'll show you how I did that. And the angularity tolerance I put on like this. And I called off and I said that I wanted that angularity within 3 in relationship to A. You know, if that would have been just a square surface, then I would have put perpendicularity. Angularity can sometimes be used in place of perpendicularity or parallelism. This one case here, I put angularity within 3 in relationship to A. So that means when it comes up to that surface, I could have a gap there within 3. So that means the rubber mounting that I have that's going to distort to be able to accept that within 3. And then what that did is that located the part fore and aft, stopped the degrees of freedom fore and aft, and now up and down I have to be able to stop it. And I said, well, let's stop the thing in that direction. And then I selected the datums and I said that it was those 4 holes. So the 4 holes just stop it back and forth. And then, of course, what I also had to do is I had to put a position tolerance on those holes. So there's my position tolerance that I have on those holes. And if you can see that there, what I did is I put a position tolerance on there within 1.8 on those 4 holes. So that's the tolerance on there. And you say, well, how did you come up with that 1.8? So let me go about and show you how I went about that, where I come up with that number. Well, this here is what I reasoned is that I have this mating part. And the mating part, what it is, I'm using 10 millimeter bolts. If I have 10 millimeter bolts, what I have to do is I have to clear a 10 millimeter bolt. So there's my 10 millimeters. And the size of the hole in the frame rail, it looked like those holes there, the smallest that hole was 12 millimeters. So if I looked at it, it had 12 millimeters. That means that I could have had 2 millimeters for position on this hole. Well, 2 millimeters position on that hole, it looks like the engineer on the frame rail, they didn't give it all. They could have had that total amount. They only gave away 1.2. So if they gave away 1.2, that means that they would have only still had 0.8 available to be able to give away, and they didn't use all of it. Now when I look at the calculations on my part, what I have is I have my bolt, and I'm trying to clear a 10 millimeter hole, or 10 millimeter bolt. So if I'm trying to clear a 10 millimeter bolt, there's my 10 millimeters that I'm trying to clear. I have an 11 millimeter hole. That's the smallest my hole could get, is 11 millimeters. So if I looked at the clearance between those, I said, well, I could only give away 1 millimeter. That's how much I have. But you notice that this one didn't use all of the tolerance. So what I did is I took that other 8/10 that wasn't used over here, put it over here, and that's where I got my tolerance inside this compartment, and I come up with 1.8. Now you said, would that work? Well, let me show you how that would work, the reasoning here behind it, and how if you have a similar problem to this, you can reason it out the same way. Let me show you how I did it. This here is the basic dimension, and I'm just going to take 2 holes. This here is the basic dimension and the distance between the 2 holes. That would be the basic dimension we had on a drawing. It was 76.2. Now right on that spot, what we had is we had those bolts, and those were the 10 millimeter bolts. We'll imagine that one is right there and one is right there. Those are the 10 millimeter bolts. Now the way we had calculated this part up on top, we said that we had a 12 millimeter hole, but what happened is they didn't use up all of the tolerance. So that means this hole was allowed to move around. It could have moved this way, the hole could have moved this way, right? And this one, instead of being basic, that same thing could have happened. This one could have moved this way to the right, and this one could have moved to the left. And what's happening is all of the tolerance wasn't used. So if all the tolerance wasn't used, we took a look at my part and I put it on. And when I put it on, what's going to happen is this part that I put on is using 8 more than what it should have used. So if it does, it's actually going to push that bolt around. So as I put my part on, as I put it on this way, it's going to actually push that bolt. It could push the bolt over here. Or if I'd put on, the holes could be off in my motor mount bracket so much that it would push the holes around. So it's going to push it back and forth. And what would it do? Is if I'm only allowed 1 and I allowed it to be a 1.8, it's going to push the bolts around 0.8. So if it pushed it around, I still have 0.8 clearance. So that's how I come up with my calculations, and I was allowed to have a 1.8. Now remember that you're allowed that amount of tolerance, but later on we can't have engineering come back and then give more tolerance on that rail. That's done. Once we calculated that tolerance, that's it. So it's a way to be able to get a little more tolerance and make manufacturing happy. We always want to keep them happy over there. Now let's take a look what else I did, what other tolerance. I also, if you noticed, put a tolerance here, down here on the location of this hole, and that would have been position. that would have been positioned within 0.5 in relationship to A, B, and C. And I put maximum material on C. That just allows the holes to move around. Remember, the alignment here is still lined up to that face. So the only thing that could happen, you know what max material on the datums would mean is that if the part actually mounted on here, the way that it would fit is that, you know, your bolts would still line up. It's just that these bolts would move. Maybe they could move over off in this direction, right? That's what MMC means, that they're allowed to move off like that. Your bolts would still, you know, everything is still measured from the virtual. So as the holes got a little larger, they could be off. So you could always still line the thing up. Let's see, what else did I do? I guess we ran out of important things to do, so the last thing I did was I come underneath here. If you notice down on the bottom here, I put a position. I said unless otherwise specified, everything was profiled within 1.5. And so that's how this part was finally toleranced to put all of our geometric tolerancing on. Do you notice what I'm trying to do on all of the parts that we're doing is they're fully geometric tolerance. So we're not using any plus or minus tolerance. And sometimes as a designer you need to be able to look at some parts. How would somebody else do all of them with fully geometric tolerance? And that's certainly the direction we're going, and you can see it's real easy to put it on geometric tolerancing and put it all over, and very clear. Set up a datum reference frame and everything is measured from that datum reference frame. That ends our motor mount part, so hope you enjoyed the problem and the solution, and we'll see you again for the next problem.